Today we're going to start Chapter 6. And Chapter 6 is all about differential equations. We're going to take a look at a couple of different ways to approximate solutions to a differential equation. Slope fields is a graphical way or a geometric way to approximate solutions to a differential equation. Euler's method is a numerical way to approximate solutions of differential equations. So today we're going to take a look at Euler's method to approximate solutions to a differential equation. Today is the 28th. And our topic is Euler's method, and it's spelled E-U-L-E-R. Okay. So Euler's method, the way it works is you're going to use the derivative. It's kind of like a tangent line approximation. And the fact that you're going to use the derivative to generate approximations. So let's say we have some differential equation that's equal to some function. Okay, a couple of givens that we need. One is that we do have the differential equation. Two is that we're going to have some starting point x0, y0. And three, we're going to have something that's called a step size. And the step size is usually noted as h or delta x. So here's our process. We start off with using our step size to generate more values of x and y. So x1 would equal to our initial value of x plus our step size, delta x. Whereas y sub 1 would be our initial value of y plus delta x times. Now here we're going to take the derivative, our differential equation, and evaluate it at x0, y0. So then to generate the next step, or the next values in this step process, x sub 2 would be x sub 1 plus delta x. Y sub 2 would be y sub 1 plus delta x times the derivative. This time it's going to be evaluated at x sub 1, y sub 1. X sub 3 would be x sub 2 plus delta x. Y sub 3 would be y sub 2 plus delta x times the derivative, or the differential equation, evaluated at x sub 2 and y sub 2. What's key here is that the y sub 1 that you're going to generate, or that you're going to use here, will be the actual value of this term here. So y sub 1 is equal to y sub 0 plus delta x times the derivative, evaluated at x0, y0. Whatever answer you get here, that's the value that's going to go in there. It's a very, very simple process. You can come across some Euler's methods that are really complex, and that you can use a calculator. The calculator that you guys have does probably have a built-in Euler's method function, but on the AP exam, those problems will always be non-calculator and they generally never go more than 2 or 3 step sizes or delta x's in order for you to solve them. Okay, so let's take a look at actually solving one of these or approximating a solution with using Euler's method. Okay, let's use Euler's method to approximate the particular solution of dy dx equal x minus y passing through zero comma 1, 0, 1, with a step size of delta x is equal to 0.1. Okay, so here the initial point that the differential equation passes through is 0 comma 1. So that's going to be our x0 and our y0. Okay. So we want to find a particular solution here of step size 0.1, and I think let's go ahead and do 2 steps here. Okay. So first off, x sub 1 is going to be x0 plus delta x. So x sub 1 is going to be our x sub 0, 0, and our delta x is 0.1, so 0 plus 0.1 is 0.1. Our y sub 1 is going to be y sub 0 plus delta x times dy dx evaluated at x sub 0, y sub 0. So we're going to evaluate this at 0 and 1. So y sub 1 is going to equal to y sub 0. Okay, sorry about that. Custodian came to clean. Alright, so we have y sub 1. So that's going to be y sub 0. Y sub 0 is 1. So that's 1 plus, then delta x, our step size, is 0.1. And that's going to be times dy dx evaluated at 0 and 1. But dy dx is x minus y. So we're evaluating that at 0 and 1, so that's going to be times x is 0 minus, and then your y is 1. Okay, so y1 is going to equal 1 plus, well, this is 0.1 times negative 1, so that's going to be a negative 0.1, and our answer there is, well, 1 minus 0.1 is 0.9. Okay, so our x1, y1 is 0.1, comma 0.9. And we're going to use these values to generate our values for our next step. So let's go ahead and do that. x2 is going to be x1 plus delta x. So x2, x sub 2 is going to be, well, x sub 1 is 0.1 plus, and our delta x is 0.1. 0.1 plus 0.1 is 0.2. Our y sub 2 is equal y sub 1 plus delta x times dy dx evaluated at x sub 1, y sub 1. So y sub 2 is equal, well, y sub 1 is 0.9. So it's going to be 0.9 plus delta x 0.1 times Now we're going to evaluate dy dx, but this time we're going to evaluate it when x is 0.1 and y is 0.9. So we're going to substitute in our dy dx here, x minus y, so that's going to be our x1 is going to, is the 0.1 minus, and our y1 is 0.9. So that's equal to 0.9 plus 0.1 times, and 0.1 minus 0.9 is a negative 0.8. So it's really important that we're real careful with our multiplications, because like I said before, most of these are going to be non-calculator problems. You do have to multiply those out by hand. Well, 0.1 times 0.8, hopefully you will get negative 0.8. So that's 0.9 plus a negative 0.08, and that value there is 0.82. So with our Euler's approximation, step size is 0.1, we can say f of 0.1 is approximately equal to 0.9, f of 0.2 is approximately equal to 0.82. If we wanted to do another step size to find out f of 0.3, we would go through this same process. But for the most part on the AP Calc exam, whether the question be as part of an FRQ or whether it's part of the multiple choice non-calculator part, they won't have you go more than 2 step sizes. Now, your homework for this section is page 411, and it's problems, I think it's 69, 71, and 73. And when you take a look at those problems in the book, they actually want you to evaluate or use Euler's method with 10 steps. So number of steps, n equals 10. But I want, instead of that, I would like for you, for each of these 3 problems, so we're not going to do n equals 10, you're going to do n is equal to 5. So your homework for those 3 problems, you're going to do at least 5 steps using your specified initial values and your step sizes for each of those. But you'll do n equals 5, not 10. Okay? All right, so that will conclude our Euler's method lesson. Period 3, you guys have a senior assembly. So just, you've already taken roll second period, so you guys are going to go over, and I think the assembly is going to take the entire period. Tomorrow, on Wednesday, we will go over slope fill, and we'll check some of the answers here with the Euler's method, and we should pretty much stay on track. Okay, so I'll see you guys when I get back.